Introduction to sequences. So we have 2 lessons to do today. We have 12 and 13, but we're going to see how we are on time at the end of 12, whether I'm going to decide we're going to do 13 or not. I don't want to overload you guys because there's a ton of vocab and stuff. It's logical, but there's somewhat of a learning curve attached to it. Okay? So it says a sequence is a very special type of a function. When students first encounter sequences, they often think of them as just a list of numbers in some particular order, and then they have to find the pattern. Okay, well, we're pretty cool with finding patterns. We will start with the technical definition of a sequence in terms of a function. So, the sequence definition. Right? A sequence is a function whose set of inputs, okay, the domain, is a subset of the natural numbers. 1, 2, 3, 4, okay? Those are our counting numbers. So it says a sequence is often shown as an ordered list of numbers, we're cool with lists of numbers, that are counting numbers, called the terms or elements of a sequence. So sequence function notation can be tricky. So that's the tricky part of it, is the notation that many times you'll kind of get bogged down with. It says, consider the sequence below. If we represent this sequence with the letter A, then do the following. So we've got this list of numbers here, this sequence of numbers, 4, 8, 16, 32, and so on. So when you're given that list, you want to try to think about some patterns, what it starts with, maybe what it ends with. So it says, find A of 3. Well, up until this point, what have we been doing? We've been taking that value that's in parentheses and substituting it into a formula, and that's our input, and then we come out with our output. So these right here, okay, these 4, 8, 16, 32, those are our outputs. So they're saying if we put a 3 in, okay, what's going to be our output? Meaning this represents A of 3 is the third term in line. So A of 3 is the third term. I'm going to pause because I got to recalibrate. Okay, so the third term in line here in my list is 16. So A of 3 is 16. Again, we don't know the rule yet. We just have the list of outputs. So now we can kind of play around with this. They're saying, okay, A of 1 plus A of 7, meaning the first term plus the 7th term. So the first term is 4 plus the 7th term is 1, 2, 3, 4, 5, 6, 7 is that 256. So that ends up giving us 260. Now, they could, again, play around with the notation. This right here, this A sub 2, A sub 2, that's how it's written, or that's how it's pronounced, A sub 2, is the same thing as this, A of 2. Just different notation, and you have to be familiar with both. So A sub 2 is the second term in line. So what is the second term in line here in our sequence? And it's 8. If I look down to letter D, it's saying A sub 1, meaning the first term, and they want us to square it. So the first term is 4, and I can square it and get 16. Find A sub 5 minus A sub 4. So the fifth term is 64 in our list, and minus the fourth term, which is 32, and 64 minus 32 is 32. So you can evaluate these values. Now, Part F is flipping that idea around a little bit, and they're saying, okay, solve for n, meaning find the number term if the term is 128. So in other words, they're giving you the output, okay? That's our output. They want to know what's the input, or what is the term number that is 128 in our line. So here's 128. There's our output. What term number is it? 1, 2, 3, 4, 5. It is the 6th term. Okay, oops, did I lie? 1, 2, 3, 4, 5, 6. It is our 6th term. The 6th term. So a sub 6 is 128. So our n is 6. Now it says sequences are functions. The key here is that the input is simply the numbers placed in line. That is huge. That is a huge understanding, so to speak. And the output, okay, is the number, the actual number in the list. Okay, highlight that, underline it, do both, because that is a huge understanding right there. Okay. Now it says, consider the sequence defined by the formula. So now they're giving us a formula for this. A sub n equals 2n plus 1. So they didn't give us the list of numbers, but they gave us the formula to generate the numbers. So here's our formula that could generate our list. It says write out, and that's what they're asking, the first 5 elements in this sequence. Okay? So if a sub 1, our first element, a sub 1, so we're going to do exactly that. We're going to say 2 times 1 plus 1, and that gives us 3. So the first term in my sequence is 3. And now I've got to find a sub 2. 2 times 2 plus 1, and that's going to give me 5. A sub 3. 2 times 3 plus 1, and that's going to give me 7. Start to see a pattern here. A sub 4. 2 times 4 plus 1, and that's going to give me 9. I bet you can make a prediction what a sub 5 is, and hopefully your prediction is 11, okay, because that would absolutely be correct. Right? So we just generated our list of numbers from the formula. Now it says, graph the sequence on the grid below for 1 is less than or equal to n, which is less than or equal to 5. So we're going to graph these. Right? And our first term, okay, term number 1 is 3. 1, 2, 3. Term number 2 is 5. 3 is 7. 4 is 9. And 5 is 11. Okay. So it says, why shouldn't we connect the points plotted with a continuous straight line? So let's think about what our outputs are right now. These are our outputs. Okay, I don't have a 3.5 in there. I don't have a term number of, I didn't put a domain in there of 4.6, okay, or 3.1. So it says, okay, very mathematically, sequences are only defined for inputs that are positive whole numbers. Sequences are only defined for positive whole numbers. Positive whole numbers. No decimals, no fractions. Okay, starting with 1. That's what we start with, our first term. Okay. Starting with 1. So keep in mind, there is no such thing as the 1.5 position in line. There's no such thing as 1.5 position in line. We have the first position, the second position, the third, the fourth, and so on. But we can't have a fractional position in line. It's not possible. So I write that down. Okay. there is no 1.5. That's just my example, or 2.5 or 3.6. Okay, position in line. Remember that input is our position, our spot in line. So it says, what is the 21st term of the sequence? Meaning, if I listed these all out, all the way up through 21, what would my number be? So it says, show your work. So this is where our formula comes in handy. And we'd say a sub 21, we're looking for the 21st position, says take 2, multiply it by the position, and add 1 to it. So we should end up with, okay, 42 plus 1 is 43. So the 21st number in this sequence is 43. Go ahead and flip that page. The sequences can be defined by a classic function formula like we saw in exercise 2. Okay, we just got done working with that. And they also can be defined recursively. Okay, there's a new vocabulary. So it says a recursive formula is one where each term in the sequence depends on the term or terms that come before it. So what do you need to remember here? Recursive relies on the term, I should make this caps, before it. Okay, recursive. You see the word recursive, you've got to think the term before. So it says, consider a sequence of numbers given by the following definition. So b sub 1, meaning our first term in line is 7. So there's our first term. And then it gives you a definition, or it gives us a formula, but this formula looks a little weird. It says b sub I is equal to b sub I minus 1 plus 4. So how are we going to generate terms in this sequence? So I know what plus 4 means. Okay, I'm going to add 4 each time. That's going to be my pattern. And what am I going to add 4 to? This right here, my friends, that b sub I minus 1 means the term, oh, big shocker, before. So let's work with this. It says, give a common sense interpretation for this, I just lost my notes, dropped my notes. 12. Okay, here we go. For this recursive function, we kind of just did that. So that b sub 1, okay, is our first term, meaning our list starts with 7. List starts with 7. And then each term is 4 more than the previous term. So each term, and after that, each term is 4 more than the previous term, meaning the term right before it. Okay. So it says, write out the rule for the first 4 terms and evaluate each one of them, except b sub 1, which is given to us. Okay, I need to create a little bit more space here. Let's see if I can shrink this down. Okay. So we know that b sub 1 is 7 because the problem gave us that. B sub 1 is 7. So now, how do I get to b sub 2, my next term in line? I've got to take the term before, which is b sub 1, and I've got to add 4 to it. So what was b sub 1? B sub 1 was 7 plus 4, so my next term in line is 11. All right, let's get the next term. B sub 3. How do I get to the third term? I got to take the term before it, which was b sub 2, and I continuously have to add 4 to it. So I'm going to say, okay, well, my b sub 2, which I just found, was 11, but I've got to add 4 to it and get 15. So what's b sub 4 then? Take the term before b sub 4, which is b sub 3, and I have to add 4 to it. So I take the term right before, which is 15, plus 4, and get 19. So right now, I have the first term, the second term, the third term, the fourth term. Guys, what's the difference between each one of those terms? 7, 11, 15, 19. What am I adding each time? I'm adding 4 each time. Okay? So it says one of the most famous of all recursively defined sequences is known as the Fibonacci sequence. Famous Italian mathematician, a gentleman right after my own nationality. Love it. It says, let's play around with this in the next exercise. So what I also want you guys to do after you finish this video is Google the Fibonacci sequence and Google, say, the Fibonacci sequence in nature. Okay, in nature. See where this sequence occurs in nature. You might be pretty surprised. It's possible. Oh, by the way, I have earrings I'll wear tomorrow that represent the Fibonacci sequence. They're fabulous. So the Fibonacci sequence is defined recursively as follows. So here's the definition. So the first term is 1. The second term is also 1. And how do we generate terms after that? It says the term is equal to the term before plus the term before the term before. Holy smokes, what does that mean? Let's see. So it says, how do you interpret this recursive rule? Write it down in your own words. Okay, so the list starts with 1 as your first term and 1 as your second term. Okay? And it's found by adding the 2 previous terms. So the following numbers are found by adding the 2 previous terms together. Mind-blowing, I know, but it's not bad. You'll see. Watch, when we start to write things down, you'll see the pattern in it. Awesome. Oh. This guy. Seriously? Just want a little bit more space. Maybe not. All right, well, I'm going to have to, let's do a little snapshot here so I've got a little bit more space. So do part B. Okay, write down the rule for A of 3 and A of 4 and A of 5, okay, and determine their values. So what did we say? According to Fibonacci, our first term is 1. But our second term is also 1. Okay, that's what it says in our definition. So how do I get to my third term in line? Well, the third term says you have to take the 2 previous terms and add them together. So what's 1 plus 1? That's 2. So now how do I get to the fourth term in line? I have to take the 2 previous terms, which is a sub 3 plus a sub 2, and add them together. So a sub 3 we found was 2, and a sub 2 was 1. So my next term in line is 3. So how do I get to a sub 5? Take the 2 previous terms, which is a sub 4 plus a sub 3. And I end up with, oops, I should put that, do I want to put that around? Nope, I'm okay. So a sub 4 is 3 plus a sub 3 is 2. So my next term is 5. Okay, so far we obviously can keep going. We have 1, 2, 3, 5. What would the next term in line be? Add the 2 right before it. 3 plus 5 is 8. What would the next one in line be? Add the 2 before it and get 13. Okay? Get the idea? All right. So let's go back so I can see where we are with this. And we are at 20 minutes. So I'm going to say we are good for right now. And next class, what we'll do is we'll talk about it. We're going to do exercise 5 in class, and then we will do lesson 13 together as a class. Okay? Nice job, guys.